Myself Haleema Saleem. I'm currently working as a researcher in Qatar University under the supervision of Professor Sayed Javed Saidi. Now I am going to give you a presentation on the topic Advanced Thin Film Composite Membranes for Reverse Osmosis Water Desalination. The outline of my presentation, which includes an introduction about water scarcity, desalination and reverse osmosis. Then we will discuss about the thin film composite membranes, its benefits and related drawbacks. Then we will discuss about some studies carried out by the Qatar University team for overcoming the drawbacks of thin film composite membranes. First study is by the Incorporation of Nano clay, and the second study is basically about a fabrication technique which is known as the spin assisted layer by layer assembly technique, and finally the conclusion. Moving on to the next slide, that is the introduction. As we all know that water is the most essential part of life, and this current world is facing the greatest challenge of drinking water shortage. As we can see from this figure that out of the total water available on earth, only 1% is available as fresh water. Remaining 97% is as salt water and 2% is locked as ice. So considering the increasing world population and with this 1% figure, it is very obvious that there is a drinking water scarcity. Now we will discuss about the global needs for water treatment. There exists some important factors such as the increasing population, natural disasters, climate change and water pollution. Drinking the contaminated water can cause different epidemic disease in the developing countries. Therefore, drinking very clean water is very, very important. Hence, proper water treatment has to be taken care of. Desalination has proved to be the best solution for the water scarcity issue. Here actually the salt water is converted to fresh water. We can see from this figure that in this process excess salts are removed from the salt water to make it clean water, and there are mainly two types of desalination technologies extensively used, that is the thermal based technology and the membrane based technology. In the thermal based technology, the multi-stage flash distillation is the most commonly used one, and in the membrane based technology the reverse osmosis is the most commonly used technique. We will discuss about the reverse osmosis technology in the coming slides. Reverse osmosis is actually a pressure-driven membrane-based process for getting pure water. As we can see from this figure that there will be a semi-permeable membrane which can be used for separating the salt ions present in the seawater. As a result, fresh water will be obtained, and there are several benefits for this reverse osmosis techniques, such as it requires only very less energy and also causes less environmental impact as compared to the other technologies. Now moving on to the next slide, different types of reverse osmosis membrane. There are basically two different types of reverse osmosis membrane, that is the cellulose acetate one and the thin film composite, the polyamide based membrane. If we consider the cellulose acetate based membrane, they are having certain drawbacks, like they are susceptible to the microbial attack, they have limited chemical stability, and also it can undergo compaction at higher pressures, whereas these polyamide based thin film composite membranes are having several advantages as compared to the cellulose acetate membrane. For example, they exhibit more flux at a given applied pressure, and they are more stable over a wide range of pH, and also less susceptible to microbial attack. Therefore, this polyamide thin film composite membranes are currently the most widely used desalination membranes. The structure of thin film composite membrane, as we can see, there will be three different layers for a thin film composite membrane. There will be a top active surface layer, which will be usually the polyamide material, and the second most layer, that is the microporous substrate layer, and mostly it will be polysulfone material, and the third layer, that is the bottom reinforcing fabric support layer, which will be usually the woven or non-woven polyester material. Now let's discuss the different benefits of thin film composite membrane. Each layer of the thin film composite membrane can be independently controlled as well as optimized. So this is one of the major feature of this TFC membrane, and also desired permeability as well as selectivity could be accomplished with the usage of thin film composite membrane, and also these membranes have good compression resistance and also have excellent mechanical strength. There are also some drawbacks for this thin film composite membrane, that is, they are very sensitive to fouling, and also degradation might happen because of chlorination, and also they have inadequate boron rejection efficiency. So it is absolutely essential to carry out studies for overcoming the drawbacks of thin film composite membrane, and also to improve the efficiency of these membranes. Scientists are continuously carrying out studies for developing the thin film composite membranes. Now let us discuss the different studies carried out by our team in Qatar University for improving the thin film composite membrane efficiency, and two different studies we are discussing in this presentation. The first study is by the incorporation of nano clays into the membrane during the interfacial polymerization process for developing the thin film composite membrane, and the second one is basically a new technique, that is the spin assisted layer by layer technique for fabricating this thin film composite membrane. Basically in this process we are depositing alternate ultra thin layers of different polyelectrolytes on top of the ultrafiltration membrane, mainly the polysulfone membrane. So there will be a deposition, the alternate deposition of ultra thin layers of polyelectrolyte on top of this membrane. So now in the coming slides we will be discussing more about these studies. Moving on to the first study, which is the incorporation of nano clay. Actually, this study validated for the first time the efficiency of two different nanoclays, that is the chlorisate 15A and the monomorgulonite. These nanomaterials are incorporated into the polyamide active layer in the reverse osmosis membrane. So here we have shown the structure of the monomorgulonite, and also listed here the different physical properties of these two nanoclays. Here we can see the structure and the preparation of thin film composite polyamide membrane. Here the three layers are observed, and we can see here it is formed by the interfacial polymerization reaction between the metaphenylenediamine diamine and the trimethyl chloride. In our process, in our study, what we have done is that we have submerged the polysulfone into the metaphenylenediamine first, and then we have immersed it into a trimethyl chloride, which is having the nanoclays present in it, and as a result of interfacial polymerization process, the thin film nanocomposite membranes are obtained. So this is actually a diagrammatic representation of the cross flow filtration system which we have done for carrying out our permeation study. Water flux and sodium chloride rejection can be assessed with this system, and the test was actually carried out at a pH of 6, a pressure of 40 bars, and at 2000 ppm feed sodium chloride concentration. And from the different graphs obtained, it was very clear that the efficiency of the thin film composite membranes are definitely improved by the incorporation of nanoclay, and this improvement is because of the increased interaction between the nanoclay and the organic solvent used in the polyamide synthesis. And now moving on to the next study, which is the spin assisted layer by layer assembly technique. Here, this is actually an innovative method for the fabrication of reverse osmosis desalination membrane. Here, basically, we are comparing the performance of two combination polyelectrolyte. The first one is actually strong polyelectrolyte combination, and the second one is actually a weak strong polyelectrolyte combination. The first one with strong polyelectrolyte combination, we use the polyelectrolytes poly diallyl dimethyl ammonium chloride and the polyvinyl sulfate as the strong electrolytes. And for the second study, we have used the weak polyelectrolyte polyallyl amine hydrochloride and the strong electrolyte PVS, that is the polyvinyl sulfide. So basically we are depositing these layers of polyelectrolyte on an alternate basis, and several layers are formed, and we are checking the efficiency of these membranes. Here, this is the AFM images of uncoated polysulfone, that is the figure A, and figure B is the strong polyelectrolyte combination, and figure C is the weak strong polyelectrolyte deposition. And these images are obtained after the deposition of 60 bilayers. So it's very clear from this picture that the uncoated polysulfone is having very porous and rough structure as compared to the images B and C, which is very smooth and non-porous structure. So this confirms the successful deposition of the polyelectrolytes on top of the polysulfone substrate. And from the permeation test results, it is seen that both the 60 bilayer and 120 bilayers of the strong polyelectrolyte can improve the water flux, but the salt rejection is not considerably improved here. But in the case of weak strong polyelectrolyte combination, both 60 and 120 bilayer depositions are showing a very good water flux as well as a salt rejection improvement. Hence, it is very clear from this study that this technique, that is the spin assisted layer by layer deposition technique, can improve the water flux and the salt rejection property of the thin film membranes. So moving on to the final slide, that is the conclusion. Our study definitely demonstrated that the thin film composite membranes are promising, and the novel fabrication technique, that is the spin assisted layer by layer technique, are also a great tool for manufacturing the reverse osmosis membrane. On the other hand, we further recommend studies to be carried out on the topic, and also studies are required on a larger scale for assessing the efficiency and sustainability of these technologies, and the key drivers for commercialization of these technologies need to be recognized for expediting the industry adoption in the near future. I would like to thank Center for Advanced Materials in Qatar University and Professor Sayed Javed Seidi for giving me the wonderful opportunity. And also I thank STEM International Organization for providing me the platform. And you may also write to me at haleema.saleem@qu.edu.qa for any information or any further discussion. I thank you, each one of you, for your patience. Thank you so much.